So welcome you to today's lecture. What I'm going to do now is I'm going to start a new topic which is on asymptotically efficient estimators. Now here the word asymptotic means as n goes to infinity, that means as the sample size goes to infinity. So first let us prepare the setup under which we want to work. So suppose you have x1, x2, xn, which is a sample. So it is a random sample from some distribution. So let me denote that by f theta, which is a distribution function. And my theta belongs to capital theta. Right? So functional form of f theta is known. That is what I assume. The only unknown quantity is the unknown parameter theta. Suppose small f theta is the PDF corresponding to f theta. And what I'm interested in is estimating g theta. So my estimand is g theta. Now this g may be vector valued also. So g may be a function from the parameter space theta, which itself may be vector valued to Rm. So suppose I want to study this problem when the sample size becomes large. So for that, let us assume that delta n x is an estimator. This is an estimator of g theta. So I have emphasized the dependence on the sample size n because I want to see the effect of sample size on the performance of this estimator delta n. Now note that this x1, x2, xn is a sample from the given population, and the sample size is n. So this only contains a partial information about the distribution or the population under study. Ideal situation would have been if I had all the information about the population under study, which is equivalent to saying that I had this n going to infinity. That means I had countably infinite number of populations, if your observations, if your population is countably infinite. So n going to infinity means I have more and more information. As n goes to infinity, that means I have unlimited information in certain sense. So the idea is what happens to this estimator as n goes to infinity? Because as n goes to infinity, this sample x contains a lot of information. So the minimum negotiable thing, non-negotiable thing which any estimator delta n is, that any reasonable estimator delta n should converge to the true quantity which I am estimating. That means it should converge to the estimand for every theta as n goes to infinity in some stochastic sense. So minimal thing expected from a reasonable estimator. What is that? That means as n goes to infinity, delta n should go closer and closer to g theta. Or in other words, delta n should converge to g theta. But note that delta n is not a sequence of real numbers, so I can talk about convergence in usual sense of convergence of real numbers. So here I have to talk convergence of stochastic quantities or probabilistic convergence. So minimum thing which is expected is delta n x converges to g theta in some stochastic sense, or some stochastic or probabilistic sense. Now, one such convergence, of course, you have studied many kind of convergence. One such convergence is convergence in probability. You can talk about convergence in rth mean, or in particular convergence in the second mean, which would be nothing but expected value of delta nx minus g theta whole square. But note that here my delta n and g theta may be vector valued. So let me write down delta n is basically my delta 1n, delta mn, because delta is estimating an m-dimensional quantity g theta. Similarly, I write down my g theta, which is an m-dimensional quantity. I write down this as g1 theta. So I'm talking about delta n is close to g theta in certain sense, in certain stochastic sense. First, let us talk about when do I say that two vectors x and y in Rm are close. Of course, one can define many distances, and each distance will give you a measure of closeness for 2 points x and y in Rm. But the most common distance is the Euclidean distance, and that is what we'll use in this course. So I define for x comma y belonging to Rm, I define Euclidean distance between them, which I denote by norm of x minus y. This is nothing but summation I is equal to 1 to m xi minus yi whole square. Now, this is called Euclidean distance because it's a distance in the Euclidean space. Now, you must have done the properties of such a distance in your course on analysis. It satisfies all the properties of a distance function. It is non-negative. It is symmetric in x and y. dxy is same as dyx, or norm of x minus y is same as norm of y minus x. It also satisfies the triangular inequality. That means distance between x and z is always less than or equal to distance between x and y plus distance between y and z. So it is a proper distance function. So we'll consider this distance function. So I can talk about stochastic closeness of delta n and g theta in terms of this distance. And that leads to the concept of convergence in probability, which you studied in your earlier course. Now, any estimator delta nx which converges in probability to the true estimate is called a consistent estimator. Okay, so let me give the definition of a consistent estimator. So consistent that means if delta n converges in probability to g theta, or for every epsilon greater than 0, probability that Euclidean distance between delta nx and g theta, the probability that this is greater than epsilon for any epsilon greater than 0, if I take the limit, this probability should be 0. So any such estimator is called a consistent. Now, this is the minimal thing I expect, because as n goes to infinity, I have a very large sample size. In fact, n going to infinity in certain sense says that I have exhausted whole the population, or I have all the information about the population, in that case the distance between delta and g theta should be arbitrarily small, or in other words, delta n should be estimating g theta precisely. So any such estimator is called a consistent estimator. Now you have studied various properties of consistent estimator. What are the properties of delta n would be consistent for g theta if and only if component-wise consistency is there. So that means delta n converges to g theta, or in other words, delta n is consistent for g theta if and only if each component of delta I is consistent for corresponding component of g theta. So if and only if delta in x converges in probability to gi theta. So this is equivalent to saying that a vector delta n is consistent for a vector g theta if and only if component-wise consistency is there. Then you know that convergence in probability is preserved by continuous function. That means if delta n converges in probability to g theta, then h of delta n also converges in probability to h of g theta, provided h is continuous. So this is remark 1. So these are the properties which you have already done. So suppose h is a function from Rm to Rp. Delta n is consistent for g theta. Then this would imply that h of delta nx is consistent for h of g theta. Right? That's very clear because you know that consistency is preserved under continuous functions. Now, a sufficient condition for consistency is that their mean square error goes to 0. So if limit n going to infinity of e theta norm of delta n minus g theta. So let me put norm of delta nx minus g theta whole square, which is same as limit n going to infinity summation I is equal to 1 to n expected value of delta I n x minus g I theta whole square is equal to 0. This would imply that delta nx converges in probability to g theta. So this provides you a sufficient condition for consistency. So if you can show that the L2 distance between delta n and g theta goes to 0, then delta n would always be consistent for g theta. Of course, the proof is straightforward. If you recall your last course, the proof is using the Chebyshev's inequality. Okay, so now let us consider a few more results. Fourth, delta n is consistent for g theta. Cn is a sequence of real numbers which goes to C. This would imply that C of delta n is consistent for C of g theta. This also follows from the results which you did last time, that if xn goes to x in probability and Cn goes to C, then Cn xn goes to C of x. In fact, a lot of other things from earlier course you can use. For example, if delta n and delta n star are two sequence of estimator, delta n is consistent for g1 theta, delta n star is consistent for g2 theta, then delta n plus delta n star would be consistent for g1 theta plus g2 theta, and so on. So now before I proceed further, let me do a few results from asymptotic statistics. Which again you have done before in a course on probability theory. So the first result which I do is about the strong law of large numbers. So x1, x2 is a sequence of IID random variables with expected value of x1 as mu, which could be a vector, and I define my x bar n, the vector of sample means, as 1 upon n summation I is equal to 1 to n xi. So it is a vector of sample means. So a strong law of large numbers says x bar n goes almost surely to mu. Of course, provided all these quantities are finite, so that means this belongs to Rp. Let us see. Strong law of large number says that vector of sample means will go to population mean, and that makes sense because as n goes to infinity, what is happening to sample means? Essentially, you are exhausting the whole population, and that is as good as the population mean. So this is very intuitive. Then there is a central limit theorem. Of course, if x bar n goes almost surely to mu, then x bar n goes in probability 2 of mu. So, or in other words, what you can see is irrespective of what the population is, sample mean is always consistent for population mean. Now, a stronger result, so such a result is called weak law of large numbers, saying that x bar n goes in probability to mu for sequence of IID random variables. That is called a weak law of large numbers. A stronger result than the weak law of large numbers is the central limit theorem, which says root n x bar n minus mu goes in distribution to np 0 sigma, where sigma is nothing but a covariance matrix of x1 or covariance matrix of any vector xi, because they all are IID. So let me call this as A part of 1, and let me call this as B of part 1. Now note that this result implies, because you know that if xn goes in distribution to x and an is any sequence which is going to 0, then xn and an will go in distribution to 0. 1 upon root n goes to 0, so if I multiply it by 1 by root n, which I get as this, will go to 1 by root n into np 0 sigma, which is a degenerate random variable at 0. So this would say that x bar n minus mu will go in probability to 0. So this result implies that x bar n minus mu goes in probability to 0, which is equivalent to saying that x bar n converges in probability to mu, and which was nothing but weak law of large numbers. That is a weaker form of strong law of large numbers. So the central limit theorem implies weak law of large numbers. Now let us consider another important tool which we do in asymptotic statistics, which is called the delta method. What I'll do is I'll do the delta method first for vector valued random quantities. So what I have is, let us say Zn, which is Z1n, Zmn, so it is a m-dimensional vector, n is equal to, so this is a sequence of vectors, and what I know is root n Zn minus mu goes in distribution to some random variable z for some mu belonging to Rn. So many times I know this. For example, I know that root n x bar n minus mu goes in distribution to z, which has a np0 sigma. I may be interested in the distribution of root n h x bar n minus h of mu. क्या हो गया? अच्छा, तो कहाँ से चालू करें? जहाँ पे रोका होता है, फिर रुकिए एक मिनट को देख लेते हैं कहाँ से. या so many times बता दीजिएगा जब करना है. So many times I know that root n x bar n minus mu goes in distribution to np0 sigma. What I may be interested in is whether root n h of x bar n minus h of mu also goes in distribution to something. So delta method actually talks about such a situation. So I have a sequence of vectors Zn, root n Zn minus mu goes in distribution to z. For example, Zn could be my x bar n's. So using central limit theorem, I know that root n x bar n minus mu goes in distribution to np0 sigma. And suppose my h is a function from Rm to Rk. With first order continuous partial derivatives. So my function h is such that it has continuous first order partial derivatives. Of course, I just need continuous partial derivatives in the neighborhood of mu. NBD means neighborhood of mu. Then root n h of Zn minus h of mu will go to in distribution to divergence of h mu transpose Z. And what is this matrix of divergence, which is nothing but del. So these are matrix of partial derivatives. So hi mu by del mu j. So which is of the order m cross k. So that this is k cross m, and m cross 1, you get a k cross 1. So this is a delta method. You see, there is a possibility that sometimes this matrix may not be non-singular. It may be singular. So then I will be getting some linear combination of z. So especially if in one dimension I am talking about, there is a possibility that derivative of h with respect to mu is 0. If it is 0, then it only says that this goes in distribution to 0 times z, which is 0. So it only says that root n h zn minus h mu goes in distribution to 0, which is equivalent to saying that root n h zn minus h mu goes in probability to 0. So I'm not getting a non-degenerate distribution as a limiting distribution. Now in such situations, especially in R1, you have a result which says that if xn goes, root n xn minus mu goes in distribution to normal 0, 1. Let me say z need not be normal 0, 1. First, I assume that h has continuous. So I assume first that, h is differentiable and h prime mu is not 0. Then using this result, I get root of n xn minus, h of xn minus goes in distribution to H prime mu into Z. Now, as I said before, there is a possibility that H prime mu is 0. If H prime mu is 0, it says that this quantity goes in distribution to 0, which is equivalent to saying that this quantity goes in probability to 0. So I'm not getting a non-degenerate distribution. So to get a non-degenerate distribution, what I should do is, because if you recall the proof is based on a Taylor series expansion. So H prime mu is 0, that means first order Taylor series expansion will not suffice. I'll have to go to higher order Taylor series expansion. So if H prime mu is 0 and H double prime mu is not 0, this would imply that root n H of xn minus H of mu goes in distribution to H double prime mu by 2. This is how the Taylor series expansion comes because of 2 factorial 2 and Z square. So the proof, as I said, is simple. It is just based on Taylor series expansion. So this was basically a brief introduction about the consistency, which is related to the concept of convergence in probability. And then we did some important results or some preliminary results from asymptotic statistics, which may be useful in the study of consistent estimators. So what I am going to do in the next module is I'll study the properties of consistent estimators. So this was all for this module, and in the next module, as I said, I'm going to study more properties of consistent estimators.